Just hold on 1 second, ये पहले restart मैं कर लूँ. So we're doing M17 and ये वाला. So let's start with this question. And with this paper. ठीक है. Ibrar, can you hear me?
Yes, sir.
अच्छा, अब इसमें ये कि starting with the first question again, it's about mainly about inorganic. तो उसने कहा complete the table showing the maximum oxidation states of all the substances. तो वो इसमें लिख लो कि what are the oxidation states. Mg is +2 obviously, Al is +3. यहाँ पे आके ना phosphorus से ना oxidation states variable oxidation states शुरू हो जाती हैं. ठीक है. Phosphorus is +3 as well as +5. Remember कि phosphorus के ना you have two different oxides. You have P4O6 and you have P4O10 as well. And not only different oxides, you also have different chlorides as well. You have PCl3 and you have PCl5 as well. अच्छा, then you have sulfur का भी issue होता है. Sulfur के भी multiple oxidation states होती हैं. The most common ones are SO2 and SO3 यानी +4 and +6. तो उसने highest कहा था maximum oxidation state. So you're going to go with +5 and +6. That's going to be your answer. So then you have explained why the atomic radiuses of the elements in the third period decreases from Na to Cl. What happens when you go from sodium all the way to Cl? Right की तरफ क्या होता है?
Proton
Why do they decrease?
proton number increases, so nuclear charge.
ठीक है. So more protons to the right. You have more nuclear charge, more attraction for electrons. So there is more attraction for electrons, and because of that, आपका और shells same रहते हैं. ठीक है. Same number of shells. So you can talk about that as well. I said then you have the radius of the most common ion of Mg is much smaller than the radius of the most common ion of S. So why is Mg smaller? The
It
Mg
has
ion.
one less shell.
ठीक है. So it loses the shell completely. Mg के outer 2 electrons चले जाते हैं, so it loses the shell. और उसने कहा much smaller. ठीक है. Compared to sulfur उसने कहा हुआ है. तो उन दोनों के differences उसने पूछा था, because there's one shell. There's a difference of one shell. Sulfur के पास पूरा एक shell extra है. ठीक है. So which is why sulfur is going to be much bigger. पहले दोनों के पास equal number of shells थे. उसका shell चला गया. तो there's a loss of a complete shell. अच्छा, फिर ये कि what's going on over here? You're saying phosphorus is a non-metal in the third period, reacts vigorously with excess oxygen, and उसने कहा some reactions are write an equation to represent reaction number 1. तो phosphorus और excess O2 है. ठीक है. Be careful with excess O2. तो उसके अंदर what would happen is phosphorus would react with O2 and it would produce P4O10. Okay? You can balance this equation. It's going to be 4P, and they're going to be 5 oxygen gas molecules. Give 2 observations you could make in a reaction number 2, ye wala. So what are the 2 observations that you're going to make?
White solid.
Okay? One of them is a white solid. PCl5, remember, is a white solid. It's very unstable. It's very reactive as well. What's the second observation? Well, what could be the
Chlorine
observation?
Effervescence.
disappeared.
Greenish yellow color of chlorine would disappear. That's another one. Name compound B. What is B? PCl5 को water में add करो, you get 2 acids. What's the other acid?
Phosphoric.
That's phosphoric. Remember, hydrolysis होता है, and it produces phosphoric acid. So that's done. Second question. There is cerium, and it's a metal. तो उसने कहा कि describe the structure and bonding in a typical metal. So and draw a label diagram to show the structure. तो उसके अंदर आपने बस वही show करना है कि what you show in O levels. That's a bunch of positive ions. All metals, they like to lose electrons in a sea of free moving electrons. अच्छा, इसमें जो words आप लिखोगे वो लिखोगे कि this is known as a giant ionic lattice. It's a regular arrangement of positive metal ions. Achha, it's a regular arrangement of positive metal ions in a sea of delocalized or mobile electrons. So that's a regular arrangement or delocalized electrons. Uske marks honge. Then you have, okay, it's a ceramic. What is a ceramic? Or कौन से 3 compounds हैं जो वैसे, I mean, although this is not in your course, but what are the 3 compounds that are ceramic and what is a ceramic material? Any idea?
MgO.
Just one second, क्या लिखा हुआ है? अच्छा ठीक, पहले तो वो है कि remember the 3 ceramic materials, so which you have to study in your course. ठीक है? MgO, there's Al2O3 and there's SiO2, which is sand. Ceramics are substances that are very tough substances. Basically, think of a very tough substance जो आप extreme conditions में use कर सकते हो, ठीक है? And those ceramics they have high melting and boiling points. So you make furnaces out of them, ठीक है? For example, MgO is used in furnace lining. They're electrical insulators. I mean, although MgO and Al2O3, although MgO and Al2O3 can conduct electricity, but because they have such high melting points that the ions are not going to move. And but that are the 2 main properties of ceramics, okay? And they're going to be insoluble. That could be a property, but these are the 2 main properties. So now you use the data to calculate the relative isotopic mass of the 4th isotope. So you have to calculate the isotopic mass of the 4th one. What is given is the AR of this entire thing. You're given the average mass of all the isotopes. So how do you calculate the relative atomic mass? What's the formula? It's the formula is that you're going to take the percentage and you're going to multiply it by the percentage abundance and multiply it by the isotopic masses. And you're going to keep summing them up. So you have an isotope which has a mass of 135.907. This one. You can find the percentage of this last isotope. How do you find the percentage of this last isotope? What do you have to do?
By subtracting
Minus
it from 100 and keeping it as X as the subject.
ठीक है, तो try subtracting from 100. इसकी क्या value आ रही है? What's the value that you're getting over here? 100 minus 88 point. Can somebody do this on the calculator quickly?
Uh, 11.114.
So you're getting 11.114.
Yeah.
And remember, you have to follow the instructions. Keep everything to 3 decimal places. So that's 11.114%. तो अब आगे कर लो कि the AR is already known. That's 140.116, and what you have to do is 0.185% into 135.907, and this is going to be divided by 100. I'm going to take the 100 over here. The next one is, so I've multiplied these two, that's 137.906 into 0.251. Next is 139.905 Mohammed, this is paper M. This is March 17, question paper 2-2. I'm just going to type it. And the last one is what is the last one? It's X times 11.114. Can somebody try and find what X is? And again, be very careful with your calculations. It's if I take everything to the other side, this entire thing would become minus. So all these values are actually negative. And then everything would be divided by 11.114.
Uh, 140.8. 140.9 is the answer.
The 3 decimal places tak karna hai. What is 3 decimal?
141.
3 decimal places.
So 140.882.
Okay, so you're getting 140.882. And again, remember one very important thing, and that is uh, when it comes to the isotopic mass, I said remember the difference between the nuclear number. The nuclear number is 136. But remember, the isotopic mass is always going to be slightly less than 136 because nuclear number is always a whole number. It just counts the number of neutrons and protons. It's always going to come out to be a whole number. I mean, 136 means that there are 136 neutrons plus protons. That's always going to be a whole number. You're never going to have half a proton. So it's never going to be in decimals. But when it comes to measuring the mass is not exactly 1. I mean, we always read that a proton has a mass of 1, but it's not exactly. It doesn't actually have exactly a mass of 1 or a relative mass of 1. And the reason for that is that masses depend. The accuracy of the mass depends on the instrument. And this could go on further if you keep on increasing the accuracy. So this is always in decimals, and it's always close to 136, but not exactly 136. Okay, so this is going to be a whole number, the nuclear number, but the mass is never going to be a whole number. Okay, the mass would always be in decimals, and it depends on the accuracy of the device that you're using. because I mean the reason I'm saying that is because a lot of people would actually round this off to 141. They would think that they're talking about the nuclear number. There's a difference between the isotopic mass and the nuclear number. Okay, the nuclear number is always a whole number. Mass is never a whole number. I mean, it could be a whole number if your accuracy is really bad and your instrument doesn't really measure decimals. Uh, Otherwise, it will always be in decimals. I said next one is explain the meaning of the term bond polarity. How do you define bond polarity? It's the unequal. I say it's the unequal distribution of electrons, of shared electrons in a bond. And what that results in is that it results in positive and negative charges. Okay, so for example, you have HF. So F is partial negative, H is partial positive. As I suggest why the boiling point of HF is much higher. So what's wrong with HF? Why does HF have a higher boiling point than all the others?
Hydrogen bond.
ठीक है, so HF has the एक mark तो ये हो गया, has hydrogen bonding. And the other one would be that hydrogen bonds, whereas the rest of them have permanent dipoles. ठीक है, so HCl, HBr, HI they have HCl, HBr, and HI have or don't have hydrogen bonding. They have permanent dipoles. Plus van der Waals forces. ठीक है, van der Waals forces are always present. Van der Waals forces are also present in HF molecule as well. And the other thing is that hydrogen bonds are much stronger, so more energy is needed to overcome them. Okay, that would be the second mark. And the relative thermal stabilities of the halides. Remember, when you're talking about boiling points, you're not actually breaking the bond. So when you're talking about the boiling point of HF, you're basically talking about the attraction that exists between the positive and the partial negative between the two molecules. You're breaking the intermolecular forces. But when you talk about thermal stabilities, you're actually breaking the bond. So when you talk about thermal stabilities of HF, HCl, and so on, HBr and HI, then you're actually trying to break the bond. So which one do you think is the strongest one?
Hydrogen fluoride.
Okay, this one is the strongest one. So the trend of thermal stabilities is going to be that it's going to decrease down the group. Why is this strongest? Because smaller atomic radius. And less shielded as well. So they're going to attract each other's electrons more. So there's more orbital overlap in the bond. And there's going to be shorter bond length because they would be close together. Orbital overlap over here indicates that because they're smaller atoms, they're going to attract each other's electrons very, very strongly, which is why the bond is going to be very, very strong. And what else? It's a shorter bond length, and that's pretty much it. More energy would be needed to break this bond. I said, then you have the equation for the preparation of hydrogen chloride using concentrated sulfuric acid is shown. And he's asking, this is a question about Bronsted-Lowry acids and bases. So use the Bronsted-Lowry theory of acids and bases to identify the base and its conjugate acid in the reaction. So who's the one who's losing the H plus one ion? If you look carefully, then it's H2SO4 that is obviously the acid. Why? Because it just lost an H plus one ion. So, and who's the Bronsted-Lowry base? That is your Cl minus one ion, because your Cl minus one ion ended up gaining an H plus one ion. So the base is going to be Cl minus one, and the conjugate acid is the reverse. The conjugate acid is, if Cl minus one is the base, then its reciprocal HCl is going to be acting as the conjugate acid. Why? Because in reverse, it's going to do the opposite. It's going to behave as an acid. It would lose an H plus one ion. So that's your conjugate acid, which is HCl. And the explanation for that would be that HCl turns into or loses an H plus one in the reverse direction. Next one is explain why the reaction. I said this one over here. Now explain why the reaction of concentrated sulfuric acid and sodium iodide is not suitable. Now this is a very typical question that is going to be asked a lot of times, and the answer to that is that what happens is that Cl minus one doesn't like to lose electrons. It's not a good reducing agent. But when you move down the group, Br minus one, I minus one, they really like to lose electrons. Why? Because they're bigger ions. I minus one is a very big ion, so it likes to really lose electrons, and it's a good reducing agent. So I can open the note summary, just one second. So in this inorganic, you have to remember what happens when I minus one and this specific group 17 reaction. You get reaction of halide ions with concentrated sulfuric acid. Sulfuric acid is a good oxidizing agent. So Cl minus one does not, only displacement happens. No oxidation reaction happens because Cl minus one, it doesn't really like to lose electrons because it's a small ion and it attracts its electrons very strongly. But when you go down the group Br minus one and I minus one, they really like to lose electrons, which is why you get a redox reaction. And the redox reaction becomes stronger and stronger. For example, for I minus one, mostly redox happens. Instead of getting a displacement reaction, the Hi or I minus one, it gets oxidized to I2 and the sulfur gets reduced to either SO2 or sulfur or H2S. So you get lots of compounds that are produced when reduction of sulfur happens. So explain why the reaction of sulfuric acid and sodium iodide is not suitable for the preparation of hydrogen iodide. So you're going to write that I minus one gets oxidized, since it's a very good reducing agent. It gets oxidized to I2, and H2SO4 behaves as an oxidizing agent. So next is about equilibrium. It's about enthalpy change. Uh, you're being asked to calculate the overall enthalpy change of the reaction. So if in a reaction your enthalpies of formations are provided, enthalpy change of formation is given for HCl, that's given, that's provided. The enthalpy of formation of the element is always zero. This is also an element, so the enthalpy of formation is zero. And the enthalpy of formation of H2 is also given. So if enthalpy of formation of the reactants and the products, all of them are known, what you simply have to do is you would have to use the formula, which is the enthalpy of the reaction is going to be the enthalpy of formation of products minus the enthalpy of formation of the reactants. To try doing that, the product is Cl2 is 0, so it's just 2 water molecules. 2 water molecules, that's minus 242 multiplied by 2 minus the reactants. The reactants are HCl, so that's minus 92 times 4, and O2 is 0. तो क्या आंसर आ रहा है इसका? What is the answer for this?
minus 116.
He's getting minus 116 kilojoules per mole. And state the type of catalyst used in the reaction. Explain how a catalyst is able to increase the rate of the chemical reaction. So what he's using copper 2 chloride as a catalyst. So what type of catalyst is this? And how many types are there?
There are two types, heterogeneous and homogeneous. Catalyst.
ठीक है, homogeneous and heterogeneous. ठीक है, the two types of catalyst. So which type is this one?
I think it remains the same after the reaction. So
No, it's going to remain the same. Like, how do you figure out the type of catalyst? The reactants are gases.
It is hetero.
Okay, so it's heterogeneous, and this is a solid. So it's a heterogeneous catalyst. That's the answer to the first part. And how does it increase the rate of the reaction? It reduces the activation energy and provides an alternate path to the reaction. So the reaction exists in dynamic equilibrium. The reaction was repeated at 1000 and the same pressure. State and explain the effect on the composition of. So he's doing 1000 degrees centigrade now, and the question is about equilibrium, not about rate. So 1000. So what's happening right now? The reaction over here is carried out at 400. This reaction, as you've already calculated, it's an exothermic reaction. So higher temperature, would the forward reaction be favored or not?
no, sir. Backward reaction would say.
Okay, so higher temperature favors endothermic, which in this case is going to be the backward. It's going to go in the backward direction. Backward reaction is going to be favored, and the reaction would shift to the backward side. So इसमें मतलब that's what you're going to write. It's going to shift. ठीक है, higher temperature favors the endothermic, which in this case is the backward reaction, and equilibrium position shifts to the left. And how would the composition change? You're going to write that there's going to be more HCl and more O2, and there's going to be less Cl2 and less H2O. So next one. Now the question is about. I mean, I need to copy just one second. What's the equation? It's 4 HCl plus O2. So that's, and it's in equilibrium with, I think, Cl2 and H2O. So probably two of these and two of these. You just let me check if this is the equation. So this is the reaction that's happening, and what is given is the initial moles. So the initial moles are provided to you. So what are the initial moles? 1.6 moles of HCl. So that's your initial moles. 1.6 moles इसके add किए, and 0.5 moles of O2 are mixed. So 0.5 moles of this. So when she's saying when 1.6 moles of HCl are mixed in a sealed container with 0.5 moles of O2. So these are the things that are mixed. So initially there is no Cl2 and there is no H2. And then he's talking about equilibrium. Then he's mentioning what happens at equilibrium. The next line states that when he does this, what is formed? 0.6 moles of Cl2 and 0.6 moles of H2O are formed. So you get 0.6 moles of this and you get 0.6 moles of this. So we need to figure out what the rest of the moles are. So you started off with 0 Cl2 and 0 H2O. You got 0.6 moles and 0.6 moles at equilibrium. That means 0.6 got produced in the reaction. And both of them, they got produced in equal amount because the ratio is the same. So if one of this is produced, one of H2O is also going to be produced. Now, apart from that, 0.6 produced करने के लिए, ठीक है, to produce 0.6, how much O2 must have reacted? Can you tell me what the value is?
So 0.3.
ठीक है, because the ratio is 2:1. So you want to produce, if you want to produce 0.6, then 0.3 must have reacted. And according to the same ratio, to produce 0.6, how much HCl must have reacted? Okay, that's going to be 1.2. Right? So 0.6 of this and 0.6 of this are getting produced. So according to the ratio to produce 0.6, 2 is produced by 1. So 0.6 are going to be produced by 0.3. And to produce 0.6, 2:4, that means double the amount, 1.2 must have reacted. So your equilibrium moles for HCl would be, you initially added 1.6, 1.2 got reacted. So you're left with 0.4. Or for O2, it's going to be 0. You started off with 0.5 and 0.3 got reacted. So you're left with 0.2 now. So you found your equilibrium moles. And he was asking for HCl and O2 moles, so we have found those. And you're given the total pressure of the container. Now, the next part is calculate the mole fraction of Cl2 and hence the partial pressure of Cl2 in the equilibrium mixture. So how do you calculate the partial pressure of Cl2? That's the mole fraction of Cl2. So how many moles of Cl2 do we have? You've got 0.6 divided by the total, which is, what's the total? 0.6, that's 1.2 and 1.8, I think. So if you do this and you multiply it by the total pressure, so partial pressure is mole fraction into total pressure. The total pressure is given as 1.5 times 10 power 5. So what is the value that we are getting for this? Can anyone try and calculate this?
So how do you get 1.8?
I mean, what are the total moles at equilibrium? Isn't it 1.8, 0.6, 0.6, and this is also 0.6. So that's a total. That's the total moles are 1.8.
Oh, okay.
I'm getting 50,000.
ठीक है, the end result is you're getting 50.
1,000.
ठीक है, that's 50,000 pascals. That's so both we found both values. And the next part is, as the next part is, he's pretty much given you everything. He's asking use this expression, the expression given for Kp, to calculate a value for Kp, state the units of Kp. So you just have to put in these values. That's it. You can find Kp. So HCl is over here. That would be done, but you have to be very careful with the calculator. Put all these values over here. O2 is over here. So start adding all these values and you can find the answer. So we're going to move to the next question. This is probably the same. What effect would a catalyst have on the value of Kp?
No effect.
So remember, equilibrium constants are only affected by temperature and nothing else. So only temperature is going to affect an equilibrium constant. Now this reaction, we're now moving towards organic chemistry, or this may, let me also open a. I said draw the displayed formula of compound P. Where is P? P is this one. So you have bromobutane. Now bromobutane and is reacting HCN and KCN with it. So what happens to bromobutane? And it's one bromobutane. So that is Br. Now halogenoalkanes undergo a nucleophilic substitution reaction when Cn minus 1 are present. Why do they undergo that? Because carbon is positive when it's attached to a Br. And when it is attached to a Br, the Cn minus 1, it comes in. And the Br is going to get knocked out, right? So that is basically what's happening here. So the Br over here, I'm just going to put a Cn instead in its place. And remember, he was talking about a displayed formula. Displayed formula can you show every single bond. Every bond needs to be shown. And every atom has to be shown. So that is what a displayed formula is. Identify the reagents and conditions for reaction 1 and 2. Now the Cn is turning into a carboxylic acid. Remember, nitriles can be turned into carboxylic acids. What you simply need to do is, if you have a nitrile and you want to turn it into a carboxylic acid, you just have to hydrolyze it. You have to heat it with a dilute acid, and that's pretty much it. And you can use the word reflux instead of heat. So reflux with a dilute acid. And what's reaction number 2? Reaction number 2 is a halogenoalkane turning into an alkene. And that is known. So let's go back. This was a halogenoalkane. This was Br. Now this is an elimination reaction. The way you get an alkene is a halogenoalkane can be turned back into an alkene, and the way that's done is when you add NaOH, ethanolic, and reflux. So under ethanolic conditions, plus reflux. And let me also we can revise the halogenoalkane reactions. This one. Let's quickly go over all the halogenoalkane reactions. So remember, halogenoalkanes had all of them. They had this partial positive carbon atom, right? Which is why, and they all had this partial positive carbon atom, which is why they all had nucleophilic substitution reactions. They had 3 nucleophilic. This is the first part. This is the formation of halogenoalkanes. There were 2-3 ways where you could form halogenoalkanes. One was free radical substitution. The chlorine and bromine UV light reaction. There was electrophilic addition of alkenes where you could have a double bond and you can add halogens to it by reacting it with a bromine or a Cl2 molecule. And then you had substitution reactions of alcohols where PCl3, PCl5, or SOCl2 could be used and the OH could be turned into a halogenoalkane. Or red phosphorus plus bromine or red phosphorus plus iodine could be used. And then you had your nucleophilic substitution reactions. उसमें क्या होता था? उसमें you had Okay, if you have a halogenoalkane, the carbon is positive, so 3 nucleophiles can attack it. It's either OH minus 1, it's CN minus 1, or NH3 minus 1. NH3 is neutral, but it has a lone pair. And every time the halogen would get substituted by these things. Uh, Cn minus 1 was ethanolic KCN plus reflux, and this one was NaOH aqueous and reflux, and this was NH3 ethanolic and reflux, or you heat it in a sealed tube. And the mechanism was important that there were two mechanisms. One was SN2 mechanism. So what happened in SN2 mechanism was that if the carbon is a primary halogenoalkane, the positive charge is very strong. Why is it strong? Because it doesn't have a lot of alkyl chains next to it, which is why it doesn't allow the Cl minus 1 to leave. So the OH minus 1 gets strongly attracted and it pushes the Cl away. So you get a transition state. What happened in SN1? In SN1, the carbon wasn't very strongly positive. Why? Because it was surrounded by carbon chains. So the Cl minus 1 was easily able to leave because the positive charge over here wasn't very strong because it was surrounded by carbon chains which have an electron donating effect. So the carbocation intermediate that is formed is very stable and it allows the Cl minus 1 to leave. Okay, next step, in the second step, the OH minus 1 comes in and then gets attracted to the carbon that is positive. So it was a two-step reaction. And then there was this last one, which is probably not, but for some reason it's probably not here. It's the elimination reaction, which is this one, which we just did. Where's the question? That if you use NaOH ethanolic and reflux, instead of a substitution, what you get is an elimination reaction. The Br and the H, they get eliminated. Now he's asking for the repeat unit of polymer Q. So what is polymer Q? Polymer Q is formed by this alkene. If you go back, but1-ene is forming polymer Q. So when you're trying to form polymers, what is the first thing that you're going to try and do? The first thing is, if you're trying to form a polymer, this is but1-ene. This is 2 hydrogens and this is 3 hydrogens. Now, when you're trying to form a polymer, the first thing that you're going to try and do is make sure you redraw this molecule. And make sure you redraw the carbon and carbon double bond. This carbon and carbon double bond has to be kept in the center. And nothing should be drawn on the left or right side of this. So there's an H on top, there's an H on top. So these are your 2 hydrogen atoms on top. This H should not be here. It should be drawn below this. It should be connected to the same carbon atom. And the same goes where you're going to bend this H and move it or push it down. You're going to bend this carbon chain as well and push it down as well. So the CH2 and CH3 are going to be pushed downwards. And this is the form of the polymer is going to take. And now the double bond is going to break and it will turn into a single bond and the carbons are going to get connected with the neighboring repeat unit and that's your molecule. So that's your polymer Q in this case. Okay, is this clear? Mohammed, is this clear, Ibrahim?
Yes.
So next is complete the reaction scheme to show the mechanism of the reaction of 1-bromo with OH minus 1 to produce R. Now this is a primary halogenoalkane. So it's going to be an SN. It's going to be an SN2 mechanism where the carbon positive charge is going to be very strong. Br would have a strong partial negative charge. Carbon is not surrounded by a lot of carbon chains, so the positive charge is going to be very, very strong. So the OH minus 1 is going to be directly attracted to this. And the Br would be pushed away. And you have to include all the necessary charges. So the next step would be you have your CH3, CH2, Br would start to leave. Here are your two hydrogens. And the OH would start to join in. And this entire thing would have a charge of -1 because the OH is -1. And in the next step, the Br would eventually take its electrons and it's going to leave. So that's the next step. And then you have include all necessary charges. So we have done exactly that. So that's it. I mean, we've drawn pretty much drawn the lone pairs. Make sure you draw the lone pairs. That's very, very important. So that's it. And you can draw the last thing. The last thing would be the Br -1 breaking off and the OH in its place. So you should draw the product over here as well. Now, next one is there's a reaction happening and but1ene with steam is shown. And so what happens when but1ene is reacted with steam? What happens is that H and OH, they get added to it. So you have but1ene. So there's a double bond over there. Now, two products are possible. Because if you add, I'm not drawing the hydrogens. If you add H and OH, the chances are that there are two possibilities. That the H might get attached over here and the OH might get attached over here. Or there's another possibility, which is that you still have 4 carbon atoms and the H gets not over here, it's the same thing. The double bond breaks, you have an addition reaction, the OH gets attached on the middle carbon atom, you get a secondary alcohol, and the H gets attached on the carbon at the end. पहले तो ये बताओ कि which one is going to be your major product in this case? Out of the two, according to the Markovnikovs rule, it's going to be the bottom one. ठीक है, because the H likes to bond with that carbon atom that's already bonded to more H's. ठीक है, this carbon over here was bonded to just one H. So the H likes to bond with the carbon atom in the double bond over here, which is already bonded to more hydrogens. So the major product is the bottom one. So it's I think, I mean, this is your major product, and this is your minor product. And then he's saying S can be oxidized, the major product. He's talking about the major product to form compound U. So it's a secondary alcohol. What happens if you oxidize it? It would turn into a ketone. The OH part is going to turn into a ketone, and ketones are resistant to oxidation. And the minor product is the first one. So the next part is, now he's saying that both S and U react with alkaline aquacidine. The reason they react with alkaline aquacidine, that's the iodoform test. Iodoform test is the test of this structure where you have CH3 next to acetyl bond O and you have a carbon chain or an H. So in this molecule over here, the ketone that you're forming, this is exactly the situation. You have a CH3 next to acetyl bond O. So the iodoform test is going to be positive. The iodoform test is also positive if you have a CH3 and right next door there's an OH carbon and an H, and here's your carbon chain. This is true in this molecule over here. In S, this is true. You have a CH3 and right next to CH3 you have a COH or CHOH. So identify the type of reaction that occurs when but1ene reacts with steam. That's that's known as hydration. And I just have a few doubts. You can also write electrophilic addition to it, just to be on the safe side, because I think he's looking for electrophilic addition as the answer. all alkenes, they undergo electrophilic addition reactions. So most likely you're going to get marks for electrophilic addition, probably not for hydration. Okay, so remember, when you're talking about the type of reaction, you have to give the type in terms of addition, substitution, elimination, or you. I mean, that's the type. You have three types of reactions: elimination, addition, and substitution. And the first part defines whether it's nucleophilic or electrophilic, or whether it's free radical. So, what can be deduced about the structure of S from its reaction with alkaline aquacidine? We've already done all of it. So, what does alkaline aquacidine tell you? It tells you that this thing is present. Either of this. There's either a methyl ketone, or there might be a methyl next to CHOH. So, you're going to write this that it contains either of these two compounds. Explain why S is the major product of the reaction. But so now this is a question on why, on the reason behind Markovnikovs rule. So I'm going to open the notes. TK, we've already done this. So probably in this. So it all depends on the carbocation stability. TK, let me open the reaction and we can talk about this in detail. Okay, why do we get a major product in the first place? TK, hopefully this opens. So when it comes to Markovnikovs rule, and let's see where's Markovnikovs. Nee, this is still. So over here, you're getting these addition reaction. Now unsymmetric alkenes, this part. So the question is, why are we getting this Markovnikovs rule? Why is hydrogen? Why do we have to look at the double bond, and why do we have to figure out where would the H get attached to? Whether it's going to be a minor product or is it going to be a major product? Why does H like to bond with the carbon that's already bonded to more hydrogens? Now, the rule is simple, but the logic behind the rule, it is that it depends on the. I would have to actually explain this all over again. So it depends on the carbocation stability. So, for example, we have an unsymmetric alkene. One carbon has more hydrogens and the other one has fewer hydrogens. Imagine an HBr molecule coming in trying to join with it. The carbon that's the H is positive and the Br is partial negative. The H is going to be attracted to the pi electron cloud, and the Br is going to get repelled by the pi electron cloud. So this is what's happening. You're getting a carbocation. Okay, so you so you're getting so coming back to this, you're going to get two carbocations. One of them is going to be look like this. Okay, I'm going to explain this in a bit more detail. So here's your H positive coming in, and here is the double bond over here. The H positive over here is going to attract the electrons. So it's going to attract and pull the electrons towards itself. So the electrons are going to get pulled. Okay, let's rotate that, and the H is going to take away the electrons, and the H would eventually bond with it. The positive charge on H is going to disappear. So that's gone. And the positive charge instead appears on this carbon atom, because this hydrogen over here stole the electrons from this carbon atom, right? The pi electron cloud is gone. And this is one carbocation. This is the more likely one. This is the major product that's going to be produced. And the other possibility is if I just let me copy paste this. So the other possibility is that the H is going to come in and steal the electrons from the double bond. So the double bond goes away, right? So that's gone. The H positive charge on H disappears. And now this carbon gets a positive charge. Now it all depends, everything depends on the strength of this positive charge. It all depends on this carbon atom in the middle and this positive charge over here, or this carbon atom over here and this positive charge over here. One of them is large, one of the charges has a very high charge density, the other one is small. This one has a lower charge density, this one is smaller. Whereas this one is relatively larger. Why is the first one smaller? Why is the positive charge of the first one smaller? The reason it's smaller is because it's surrounded by more carbon chains. There's a carbon chain on this side and there's a carbon chain on the other side as well. So carbon chains have an electron donating effect. So the carbocation has more carbon chains, more alkyl chains. This positive carbon atom is surrounded by carbon chains. So the positive charge becomes smaller because it's getting electrons from all sides. On the other hand, you have a carbon which is positive over here. This is not surrounded by a lot of carbon chains. There's only a carbon chain on one side. So which is why the electron donating effect is not there. It's not that large. So since the positive charge is strong, what would happen over here is that this ion is going to be unstable. It's very unlikely to form. And why is it unlikely to form? Because if the positive charge is so strong, the electrons that the H was trying to steal, I mean these electrons over here, H was trying to steal those electrons. Those electrons are going to get pulled right back. And the double bond would reform. And the positive charge is going to go away. And the H would not be able to steal those electrons. So the thing is that the reaction would not be able to happen in this case. Because if it happens, and if the H is able to manage to steal those electrons in the double bond, the carbon gets a very strong positive charge. And the strong positive charge is going to pull those electrons right back. So no reaction happens in this case. Or the chances of a reaction happening is very, very little. Now over here, since the positive charge is small, so it's not going to pull these electrons back. So the H would be able to take away the electrons and bond with this carbon atom. And this positive carbon atom can wait for the Br-1 to arrive. And then the Br-1 comes in, so it can easily form a new bond. But it wouldn't be in a hurry to form a bond. But over here, the problem would be that the positive charge is very strong. And it wouldn't allow the H+1 to take electrons from the double bond. TK, is this clear? Mohammed, is this
Yes.
clear? So the answer is the paper. So the answer that you're going to write is you're going to talk about the carbocations that are going to be formed. You're going to talk about the secondary carbocation that is formed, or you can draw the shape of the molecule. I mean, you can simply draw whatever we have drawn over here. You can draw the shape of the molecule, and you're going to talk about the stability of this carbocation. It has more alkyl chains, hence it's more stable. That's it. Draw this molecule, draw this particular ion, tell them that it's a secondary carbocation. The secondary carbocations are more stable, they're more alkyl chains, which have electron donating effect. So the charge density is lesser. That's it. So this is what you're going to write over here. Haji. I can't hear you.
Can you hear me now?
Huh.
Acha, so I was thinking we write ke according to the Markovnikovs rule, hydrogen likes to bond with a carbon that is already bonded to most hydrogen atoms.
Lekin he's asking for the explanation behind that. No? I mean, look at the question. He's asking, okay, why is it? Explain why S is the major product. I mean, you've already, but you don't have to state the Markovnikovs rule again. you have to explain it. So you're going to draw this molecule or draw this ion, okay, and tell them that a secondary carbocation is a lot more stable because of the greater number of alkyl chains around it, which have an electron donating effect. Okay, let me write down the answers over here as well. Okay, you're going to talk about. I mean, it would be better if you. What's the molecule? So this is our. This was our carbocation, right? So you're going to talk about secondary carbocation being more stable. So it's more stable. The more alkyl chains. Which have electron donating effect. And this is what makes the carbocation stable. I mean, that's pretty much it. We've written that as well. So that's about it. That's your 2 marks. So we have to draw the skeletal formula of S, T, and U, so we can do that over there. This is 4 carbon atoms, so that's 1, 2, 3, and 4, and there's a ketone on the second one. That's your carbocation. We can draw the rest as well. This is 4 carbon atoms with the OH on the second one. So write a equation to represent the oxidation of S. You can do that. It's so is there any other question? Let's try and complete this paper completely. You have this molecule and it is a colorless liquid. It's an acid. It reacts with methanol in the presence of an acid to produce a named compound V. So it's an ester. It's obviously an ester that's being produced. And he's reacting it with methanol. So it's CH3, and there are 3 CH2s. Plus there is C double bond O and OH. And the other one is methanol. Methanol has just 1 carbon atom, so that's OH. And this carbon would have 3 H's. Now, the OH and the H would be lost. And when they are lost, they're going to get connected together and they're going to form an ester. What would be the name of this ester?
Methyl pentanoate.
Okay, so this side, it's going to be named in 2 parts. This side is meth. This has 5 carbon atoms, that's pent. And this side is vial. Okay, the alcohol side is vial. And then he's talking about infrared spectroscopy, I think. So he's saying a student analyzed pentanoic acid, methanol, and me using infrared spectroscopy. The spectrum will return to the student without labels. Identify which of the infrared spectrum corresponds X, Y, or Z. So there's probably some. So they're drawn over here. So remember, one of them is a carboxylic acid, one is an alcohol, and the other one is an ester. So you're given 3. So we need the data booklet. Where's the data booklet? 1 second. So infrared spectroscopy. This one. Now, which bond? Carboxylic acid has an OH bond, and it's easily identifiable. There's going to be a strong and very broad absorption at around 3000. So go and have a look which one is carboxylic acid. Strong and very broad absorption around 3000. This is definitely not. It's not carboxylic acid, right? So that's definitely not carboxylic acid. Strong and very broad absorption at around 3000. So this one kind of looks like a carboxylic acid. Because it's a strong and broad absorption. This one is further away than 3000. So this is probably just an alcohol. Because remember, if you look at the data booklet, you would notice that normal alcohols, they have absorptions above 3200. Carboxylic acids, their absorption, strong and very broad, starts somewhere below 3000. So by just looking at the spectrum, this one is much further away than. I mean, you can clearly see that it's higher than 3200. So probably an alcohol. This one is lower than carbox or less than 3000. So that's probably a carboxylic acid. And that leaves you, and always remember, this is going to be a serial bond O, because it has a very unique absorption at serial bond O is very easily identifiable. Around 1700 and 1600, you have a very, very strong absorption. So that's definitely serial bond O. That absorption is missing in the alcohol because the alcohol doesn't have a serial bond O. And this one must be an ester because the ester has a serial bond O, but there is no OH. I mean, no absorption for OH. So that's the only one that's left. That must be an ester. ठीक है, ये clear है? So it's a 4-mark question. You're going to identify each one of them. ठीक है, you're going to write. You're just going to quote values for this. You're going to quote values. For example, look at infrared spectrum X. There's identify this absorption. So there's serial bond O in this, right? But there is no OH because there's no strong and broad absorption at below 3000, and no absorption above 3200. So no OH. So you're gonna quote these two things. So it must be an ester. How did you figure this out? There is no serial bond O over here in Y. No absorption at 1600. But it must be an alcohol because there's an absorption above 3200. And this one must be a carboxylic acid because there's a strong absorption or broad absorption at below 3000. And it also has a serial bond O. Okay, Mohammed, is this clear? And I think that's the last part.
Yes.
So let's continue tomorrow then. Okay. Okay then.
Thank you.
Take care. Bye.